Hello and welcome to something that I'm sure you're going to find very useful and very relevant to your day-to-day lives, which is going to be electrical circuits. So electrical circuits are something that have been around for a little while, but only really became very, very useful in the past 100 years or so with the advent of computers. So the first thing that we want to do when we talk about circuits is define the term current, where current is going to be delta Q over delta T. Oh, and I might have forgotten to define that uh, the units of uh, charge, which are Q, which is Q, is given by coulombs. I might have forgotten that in my last lecture. But uh, current is how much charge flows through a area uh, in a given amount of time, and its units are the ampere, which is 1 coulomb per second. So what happens is that there are two main source types of uh, voltage to apply. One is a direct current, and one is an alternating current. Direct current was uh, proposed, or not proposed, but a big proponent of it was Thomas Edison, and then the big proponent of alternating current was Nikola Tesla in the early 20th century. So, uh, direct current is pretty simple. You just apply a voltage, uh, which is a potential energy difference, right? Or it's related to potential energy. So you apply a voltage on either side of a wire or whatever piece of electronics you're looking at. And then that's going to create an electric field, which is going to drive forward the uh, electrons in the diagram because voltage is related to electric field in the same way that force is related to energy, and in the same way that potential energy can cause there to be a force to drive forward something. Potential voltage can cause there to be an electric field, which is also going to apply a force over to an electron. And then an alternating current is one where the current goes up and down and up and down. So rather than going straight through the wires like you see on the left-hand side, as the voltage goes up and down and up and down in this sinusoidal pattern, the current inside of the wires and inside of the electronic components goes back and forth, and it's easier to, for one, carry information this way, and it's also tends to be a lot more power use, or a lot more useful for high power transmission of signals over far distance. So like what you'll usually see is that your or your, not your phone lines, your electricity lines come in with AC, and then somewhere in the house they're converted to DC currents because those are generally a little safer. But this is 100% just me going on a rant about Edison and how Edison killed elephant because he wanted to make people scared of how dangerous AC current was. So going forward, we have Ohm's law, which is V equals IR, where voltage is equal to the current I times the resistance, which is measured in ohms. So current times ohms is equal to voltage, which is going to be let me just talk about the units for a second. The unit of the volt is going to be equal to the unit of energy divided by Q is equal to a joule per Q. And then I, the current, the unit of I is equal, or joule divided by coulomb. But I is equal to current per time is equal to a coulomb per second. So the unit of R is equal to joule seconds times coulomb squared, which is also just called an ohm. And then an ohm tells you how hard it is to push current through a certain object. So the resistance means that twice as high of a resistance means that it has half as much current flowing through it, and 3 times as much means it would have a third as much current flowing through it. But that's we're just going to go over some like basic circuits. So this is first off, because it only has, because it's dependent on the electric field and not the force, or it's dependent on the electric field slash voltage and not the force, it's just assuming positive voltage would mean that there's a positive current, which means that a positive charge was flowing through the circuit. But we know that this isn't the case, because usually what flows through a circuit is going to be an electron. And if you'll remember your chemistry or science classes, an electron has a negative charge. We also talked about this briefly when we were going over the difference between positive and negative charges. So if you have a current going counterclockwise or going clockwise like you see here, then the actual flow of electrons is going to be in the opposite direction, because current assumes a positive charge and for a positive voltage, whereas electrons are actually negative. But anyways, you have this electrical circuit where we bring it up by comparison to an analogous water circuit, where the battery, which is the V, which is this section here, is just going to be represented by a pump, and a resistor is represented by a sand filter that makes it harder for the water to get through. And then the ground just refers to the fact that the system has one section that's just buried into the ground. So this is the bottom prong you'll see of your the bottom prong you'll see of your electric doohickeys. So all of your electric things have the two prongs coming out and then a bottom prong, which is just something that you plug into the wall. And then the bottom prong is plugged into the earth because the earth doesn't have a lot of electrical mishaps that can happen with it. So by keeping part of it at the same potential energy as the earth, you're able to make it a little bit safer and not have those weird power spikes. And then for the just a battery and a capacitor, basically that's similar. The valve is similar to a switch, or the switch is similar to a safety valve. The battery is again a pump, and then this time the capacitor is analogous to a stretchable membrane. And then, so resistors can also come in something called series and parallel. So a series is if you add all of the resistors together so that as the current goes through them, like you see in this box, it goes from the voltage across one resistor, across the other resistor, and across the third resistor, all in a row. And what we found is that this is equivalent to just going through one resistor, where the equivalent resistor is just equal to R1 plus R2 plus R3. So if one of them's 1, the other one's 2, the other one's 3, then this would have a total resistance of 6 ohms. However, if you have something called a parallel resistor, which is instead of current just going through all 3 resistors in a row, you have it set up so that the current passes through each resistor at the same time as it splits off into different currents with different charge passing through them. And then this can also be an equivalent resistor, but instead of being just adding them up, you add up their inverses. So 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So 1 over 1 plus 1 over 2 plus 1 over 3 is going to be equal to 6 over 6 plus 3 over 6 plus 2 over 6 is equal to 11/6. So R equivalent actually goes down and is equal to 6 over 11 ohms. So that required a little bit of algebra, but basically I was just trying to demonstrate what happened if you added up the equivalent resistor for series and in parallel. And actually what's kind of interesting is that if you do the opposite, if you use capacitors, then the opposite rules will hold true, where the equivalent capacitor for one in series is just or a set of capacitors in series is just going to be the capacitances added up. And the equivalent capacitor for capacitors in parallel is just going to be their inverses added up, like you see, or the capacitors in series is going to be their inverses added up, like you see for resistors in parallel. And I think that might be it. Yeah, so that's going to be it. Thank you for joining me today, and I'll see you again soon.